there is just deformation in one direction. The same way, if we have shear wave, now we have a strain which is just a distortion strain, and in this case, which strain is that? Can you tell me which shear strain we're talking about? So it will be epsilon.
X is, so it's moving around direction 1.
And
the strain is in direction 3. So it would be what, 1, 3?
1, 3 or xz, right? According to this coordinate system. So there is a strain just in xz. There is no shear strain in yx. There is no shear strain in yz. There is just shear strain in xz. And because this is just also a pure shear strain deformation, the shear wave velocity is going to be simply g divided by density. And the wave travels in this direction, and if this is the undeformed solid, when the wave passes, it deforms the solid like that. I forgot to do something. That reminds me that for this kind of deformation, what you get is a deformation which is something like this, the same thing that we just observed for shear wave. So very similar. Well, it's actually the same. There's just one subtle difference. Yes?
So I was going to, moving into physical descriptions, the shear wave is a transverse wave, and the P wave is a compression or rarefaction thing.
Yeah, or a longitudinal wave, some people call it. It's very important here to remember that the P wave, it's only possible in a three-dimensional solid. It's not possible in a one-dimensional solid. That's another thing. For example, if you have like a long rod that you hit it with a hammer on one side, the rod is going to be able to expand to the sides, right? Like the same test that we did for measuring Poisson ratio. If it can expand to the side, that's not a P wave. It's also a longitudinal wave, but it has another velocity. Actually, that's a rod wave, and it's proportional to the Young modulus and not to the constraint modulus.
But in a rod, if a general wave like with spring is so high, the wavelength is so short, it can become like P wave for a short time, right?
I don't know that. You know that? I think you probably know more about this than anyone here.
We did it all the time. Right?
So
generally the P wave, very high frequency.
yes.
So it starts not like the whole rod will compress. It's just a point that compress. So like it's
Okay.
waveform. So it's kind of like P wave.
Okay.
It's like wave.
Your phone, I think, doesn't like your opinion, but I think you're right. Yes. But there is a conceptual difference, right? And it's very important, especially in continuum mechanics, that you consider the right boundary conditions. If you don't consider the right boundary conditions, you're not going to be able to solve your problem. Let's see, what time is it? Yeah, 3:11. So probably in order to close here the topic, I have to mention this. I have given you data of density, of wave velocity, which is what we just discussed here. So P wave, shear wave, that's what you have over here. Remember that here you have the reciprocal, which is what you often report in petroleum engineering. Yes?
That unit is microseconds?
Correct. That's microseconds per foot. So that's a typical unit in geophysics and petroleum engineering, wellbore geophysics, right? And I recommend that you work in the international system units. So convert all of those to meters per second. And this one to kilograms per meter cube. Okay, so there is actually a problem here. And the problem is that these ones are called what some people call a dynamic measurement. And they're called a dynamic because it's a measurement of a wave. And it usually involves very small strain. However, the horizontal stresses are a result of stress building up over thousands of years. And that stress, we'll call this the Young modulus that you get from here is going to be a dynamic Poisson ratio and a dynamic Young modulus because they are determined from waves. However, in order to compute these stresses that build up over thousands of years, or sometimes if you want to compute the stress change during the course of reservoir depletion or to completion, a few days, a few years, it's also not going to be the same. You want to need for this what are called the static Young modulus and the static Poisson ratio, which these two are not the same. Okay? We're going to explain in detail later why they are not the same. But everything you have to do right now, or to know right now, and for this simplified homework, and actually it's a simplified assumption, but many people use it a lot, especially in industry practice, is you're going to say that actually our unknown is the static modulus.
You're going to assume the Poisson ratio is the same static or dynamic?
Yes, we're going to do that. We're going to assume those are the same, which is a reasonable assumption for small strains. And we're going to say that the static modulus is going to be a fraction of, I think sometimes called this FD or F or FSD, static to dynamic, of the dynamic, where that's going to be a constant number. And for this example, you have it over here, right? 0.65. Usually the static modulus is smaller than dynamic modulus. And that's linked to the magnitude of the strain and also to the strain rate. Those two things are going to determine what this coefficient is. There is one more thing that you have to do for the homework, and is, you see this over here? In this case, we're assuming what is called a tectonic strain. And that tectonic strain is going to come from the solution of this same problem, but assuming that these two are not zero anymore. And now these are given, these are prescribed, and often in geological models, these are calibrated with field data. So you don't know what they are, but you know what they cost. So you calibrate them, you find what is the best solution for this to explain what you see in the field, and that's how you get them. But that's the only thing we're missing. Okay? So we're going to do that on Thursday, and I'll see you then.